Hi, my name is Jim, and today's topic is FM reception. And we're going to start by talking about the additional stages that an FM receiver has in addition to that of an AM. And first we're going to come off a standard RF mixer IF front end on this. So the front end of an FM receiver looks like that of an AM, except the frequency for commercial is significantly higher. It's approximately 88 to 108 megahertz. Now, when we're talking about super heterodyne receivers, what they do is they take a channel on assigned frequency and down convert it into an intermediate frequency. And the reason it's called intermediate is because we want to get it in the baseband, which would be, say, like an audio signal or a video signal. So the intermediate frequency is halfway, we'll say, between the frequency off the air and the baseband signal. So all it does is it translates that signal, it brings it down in IF. It does not alter the sidebands, with the exception for high side of reversing the upper and lower, but that's not of significance if we're not working with signals that are polarity dependent, and audio is not one of them. So on a satellite receiver, it's also a super heterodyne, except for one tuned station. It takes a block of frequencies, a low noise block converter, and converts it down into frequencies maybe up to a gigahertz. And that is so that the high frequencies coming off the satellite, if fed into a typical cable TV RG6 cable, wouldn't be attenuated to death before it got to your television set. So it's actually taking a band and moving it down. Again, doesn't change anything. So anyway, this is the front end, and what we're going to do here is introduce another stage called a limiter. And depending upon the receiver design, this may or may not be required. These here are both tuned to 10.7 megahertz, which is the standard intermediate frequency for an FM receiver. It is coupled into a discriminator, and here we see what's referred to as an S-curve, and what comes out of that is audio. Now, in addition to audio, there are other things in a commercial band, but we won't detail that till a little bit later. So let's talk about the limiter a little bit. And sometimes discriminators can decode AM. They can detect it. And what that looks like in the signal is noise. So what a limiter does is it removes any amplitude variations in the intermediate frequency. Now, if we have a standard audio amplifier and we overdrive it a little bit, we're going to get clip, and that's bad because it introduces distortion. If we have a limiter, we get severe clip, and that's good because basically we cut the top and bottom of the waveform off where any variations in amplitude would live. So here I've got a incoming intermediate frequency signal, and it's kind of designed to show you that there's all kind of variations in amplitude. Part of that is due to incremental AM, which is part of the FM process, and the rest of it has to do with, say, lightning, flicking on and off light switches, car ignition, and so forth. So this is fed into a limiter which severely clips it, and what we're seeing here is the output kind of looks like a squarish waveform, and it's basically the same amplitude. So going into the limiter, or coming out of the limiter more correctly, is we have this clipped signal here, and then when we filter it here, what we end up with is a 10.7 megahertz sinusoid. Now the reason that is because coming out of the limiter we have the 10.7 and a whole bunch of harmonics over here. The output tuned circuit of the limiter basically would look like this, and filter out the upper frequencies. So we end up with a nice 10.7 megahertz sinusoid. And when I say sine wave, that's not exactly true. If it's being modulated, it's actually not a sine wave. For example, the phase is going to change a little bit, which means it's not truly a sine wave, and that can be evidenced by the fact that there are sidebands associated with FM when it's being modulated. So that's our limiter stage. Now let's move on to the types of discriminators. Now a little story here. Major Armstrong discovered FM, and he went to the RCA, Radio Corporation of America, in the 1930s, and they were kind of like the Microsoft of the day. And the Bill Gates equivalent was named David Sarnoff. And Armstrong thought it would be well received. Here he had come up with a radio transmission scheme which was very much, had a very better signal-to-noise ratio, but RCA wasn't interested. And the reason was that they were investing in television receivers very heavily. So in the end of the 30s, they actually were selling television sets, and there were very few transmitters around, and the television sets basically had, from the standpoint of video, about 4 megahertz, and then sitting outside of that was a separate transmitter. So this would be the video information, and this would be the audio information, and that was an amplitude modulated sound system. So World War II came, and manufacture of radios and television sets was basically curtailed. And after the war, because of noise interference in AM, the FCC mandated that the carrier in this be frequency modulated. So people, not many, but people bought the sets with AM detection. So to make their sets work on FM, they called technicians out, and all they did is mistune the intermediate frequency stages. So ordinarily, the intermediate frequency would be exactly in the center of the response of the intermediate frequency amplifiers. Now it's broader like this, and I've just shown it like this here for the sake of ease. And by mistuning it, the intermediate frequency locates on the slope of the response curve of the IF. And then if I take a sinusoid shown as deviation here and project that onto this slope, is what we see is we can recover that signal which caused the deviation as an audio signal. Now the problem with this is this curve from here to here is not straight. And what that means is that the audio coming out is going to have a degree of distortion. So it did work, but further development was needed. So another common discriminator topology was the Round-Travis, and this is kind of easy to understand. Here we've got a 10 megahertz primary, and there's 2 secondaries on this. One is tuned slightly above, and I've indicated 10.8 megahertz, and the other is tuned slightly below. I've indicated 10.6 megahertz. And this goes into a detector network. And basically, if we take the superposition of these 2 tuned circuits, it kind of looks like this. Now, if I draw a straight line through this, that is what I want to do, is to have a very linear transfer curve. And then if I were to, say, do a projection on this, projecting that off the top and off the bottom, it would give us a pretty linear response. I worked on a frequency modulated microwave for voice transmission, a lot of voices, 600 channels as a matter of fact, and it had one of these guys, and part of the lineup procedure was to tune this within 2% linearity. And I had a lot of trouble, and I was new on the job, and then I read the instructions. The AFC was turned on. So every time I make an adjustment here, it would shift the local oscillator. There's a message in there somewhere about instructions. Other types, Foster-Selu is very common. That's a high-quality detector. And then a less expensive ratio detector, which is self-limiting, found its way into early television sets and some FM radios. So we can also detect frequency modulation by using a phase lock loop. That's a PLL, is abbreviated. And inside of a phase lock loop there are 4 blocks. Well, one is a phase comparator, the other is an amplifier, another is a filter, and it feeds back into a voltage controlled oscillator. Now, as I've drawn it, the amp and the filter may be reversed, but the spirit's the same. So what happens is we set the VCO to a free-running frequency, which, say for detecting FM, would be 10.7 megahertz. Then we apply the signal here. Now, the VCO is not locked to the input signal, so it's going to be off a little bit in frequency, and the phase comparator will generate an error voltage, which will be amplified, some of the noise taken out, and a correction voltage applied to the VCO, which moves it toward the frequency of the incoming signal. So when it gets to the frequency, the output of the phase comparator is basically going to be an error voltage, which is maintained to lock the VCO to the signal input. Now, as the signal input frequency changes, the VCO will track it. And that's because of the error voltage. Now, the interesting thing is when you apply the signal, the VCO doesn't necessarily immediately move toward the frequency of the signal. Sometimes it moves away and comes back. It's a complicated relationship when the signal's applied, but ultimately what we want is lock. Lock means that the phase output's going to be a little bit different, but the frequency is going to be exactly the same. So if we take a look at a phase lock loop, and here's the transfer function, I've drawn that as a straight line, and basically this is the linearity of the VCO. Now let us pretend that our signal in here is just going to be a signal generator, and I'm going to start to turn up the frequency on it, and here's 10.7 in the middle. So what's going to happen is that as I turn the frequency up, I'm going to get to a point here where it's going to capture. And then as I continue to increase the frequency, it's going to follow down here until I get to this point where it's going to break lock. So this would be the capture point, and then this would be the loss of lock point. Now what you need to know from this is that the capture point is inside of the lock point. This is going to be the lock range from here to here, and the capture range is smaller. And then when I get up here, continuing to increase the frequency doesn't produce any other useful results. Decreasing the frequency, coming back, is it'll lock at this point. So I would have a line coming down here, it would follow up the curve to this point, break lock, come back over here. So this is going to be the voltage output, and this is going to be the frequency input. Now what I've done is I've located our intermediate frequency directly here, and that should be the frequency at which the VCO free runs. Lock occurs, we're sitting here, and let's just say we don't have any errors in the VCO and the phase comparator. The free running frequency of this is very, very close to this. Now as the signal deviates, I can do a projection off the voltage controlled oscillator characteristics, and from that projection I can see that the output voltage is going to be a function of the modulating voltage, just like before. So the claim to fame of phase lock loops is that they're very simple. They don't have any tuning other than RC, as resistor capacitor tuning of the VCO, and once you achieve lock, ideally in the center, because you want the VCO to be center of range relative to your maximum deviation, you're in good shape. Now if the thing is over deviated and exceeds the capture range, then the phase lock loop is going to lose lock, and our output signal will look very bad. So, as you can probably imagine, if we increase the magnitude of the modulating voltage and do that projection off of the VCO characteristic, we'll see a sine wave out here which is larger in amplitude. So, the amplitude is a function of how much the carrier signal is deviated. The frequency is how fast it's deviated back and forth. 2 kilohertz deviation, we'll say, would have one complete sinusoid inside of a half cycle of 1 kilohertz for deviation. So phase lock loops were first used, by the way, in 1939, surprisingly, to decode AM. And it was called a homodyne, and it's capable of much less distortion. And unfortunately, back in those days, it cost a lot more money, so it was not used. Now we can also, and this is just an aside from FM detection, use a phase lock loop as a frequency synthesizer. And the way we can do that is by putting programmable divide-by stages on the input to the phase comparator and in the output of the VCO. Now what that allows us to do, say for example on our car radios or anything else with an up-down channel changing button, is when we push it, we change the local oscillator frequency for FM exactly 200 kilohertz. So it's always on station, and this is crystal referenced. Likewise in television, and I'm talking about digital television, when you up and down channel change on your remote control, you change the local oscillator frequency by 6 megahertz. Exactly. There's never any fine-tuning anymore on synthesized receivers. Okay, let's take a look at an output of a stereo FM receiver, and this would be coming out of the discriminator, and this would be before the stereo processing and SCA processing, and this is referred to as the baseband signal. This is the entire signal that frequency modulates the FM transmitter. So let's take it apart, and like I said, this is stereo. In the beginning, we have a left plus right signal, which simply means that the left and right are added together. You can do that with 3 resistors. It's a linear addition, and this would be the monophonic component, so that non-stereo radios can receive standard broadcasts. Also sitting up here, we have a 19 kilohertz pilot. That's very important, and that does 2 things. First, it turns on the stereo light on your receiver, which on larger ones they have, and secondly, if we take this and double it, it's 38 kilohertz, and it becomes the carrier for this guy. Now, sitting up above that is a left minus right, suppressed double sideband suppressed carrier AM signal. Now, this is going to be, the center of this is 38 kilohertz, and this is going to be 38 kilohertz minus 15K, and 38 kilohertz plus 15K. So here we've got our high fidelity embedded right into the system. We cannot decode a suppressed carrier AM signal without a carrier. So the 19K is simply doubled in frequency, which is very easy to do, reinserted into this, and then this would go through a standard AM detection where the carrier frequency would be 38 kilohertz. So what does L minus R mean? And simply is that the audio from the right channel is inverted by 180 degrees. So that's the way we get stereo here. Now we got to do a little bit more work on them coming up. In addition to that, we have an SCA, or may have, not all stations have them, and that stands for Subsidiary Communication Authorization. And an example of use for that would be, say, the Society of the Blind offers blind people radios that detect this, and then they can read newspapers to blind people, and canned music, elevator music, whatever you want to call it, store music. And this here is a frequency modulated signal. The carrier is 67 kilohertz, and it's only permitted to deviate 7.5 kilohertz. So this is relatively low quality compared to the high fidelity part of the signal which resides up here. So a bit of deviation is used for this SCA channel riding on the baseband signal. Now, how much stuff can we stick on here? Well, some of the deviation that's used means that it's not available for this, and what we saw on the previous page is that the audio output is proportional to the deviation. So what that means is the audio output will be a little bit less, which means it'll be closer to the noise floor. So this is not free on board. There's a noise penalty to pay for this. And the interesting part about this is all of this is frequency modulated, and the baseband contains a type of amplitude modulation, and in addition to that, there's also a frequency modulated carrier which is frequency modulating the main channel. So there's some pretty cool stuff in there. And then to pull this off, by the way, all you'd have to do would be at this point, coming out of the discriminator where all this is located, is have a tuned circuit, 67 kilohertz, get rid of this stuff, feed the output of that tuned circuit into a discriminator, phase lock loop if you will, whose free running frequency of the VCO sits at 67 kilohertz. You got your audio output. Not very hard to do. So as far as this is concerned, this is fed into the stereo processor, and in the output are going to be audio signals that I've designated as left and right. Now, how complicated can it be to get that? So let's take a look at this. And this is an inverting summing amplifier, and this is just an inverting amplifier. I really don't need this, but I'm going to do it because it makes the math nice. Feeding into this we have L plus R and L minus R, and this here linearly adds them together. The gain of this stage here is -1. That's from either input to the output, so -1, and that just means the phase is going to be inverted by 180 degrees. And then the gain of this stage also is -1. And the equation to determine the gain is -RF over RI. And since these have the same values, it'll be -1. So sitting over here after this double inversion here, as I can see, if I just add these two signals together, is what I end up with is 2L. So 2 times the left audio signal comes out of this circuit. Now the only reason this is here is so I don't have to deal with a negative out here, which would be confusing. Actually, if I didn't put this on and I didn't put this on, it wouldn't matter. As long as the phase of the left channel relative to the phase of the right channel is close or exact, we'll say, all is well. The absolute phase here relative to being what's transmitted is irrelevant. The reason is it takes time to get from the transmitter to here, which causes a delay in the signal anyway. So this is just done for convenience so I can show the 2L part. Now let's take a look at the L minus R. And just remember that the -R means that it's 180 degrees out of phase. So we're going to go through an inverter here, and what we get out of the inverter is -L plus R, and here's L plus R. And then we're going to add them together. Coming out of the inverter is -L plus R, L plus R, and then we're going to add them together. And then we're just going to invert them again. And now when we add things together, is what we see we get out of this circuit here is a 2R, 2 times the right channel. So we've in fact separated the left and right channels by using simple op amps in inverting and summing configurations. Not hard to do. So for a good stereo soundstage, and what that means is the separation between the left and right channels, the signal delay through the L plus R and L minus R processing steps has to take the same amount of time. And if there's any time difference, that stereo image disappears. So there are delay lines to slow down the L plus R because the L minus R has to go through additional processing. Under good circumstances, there will be about 30 dB separation between the left and the right channel. Now while we're here a little bit, cellular telephone basics. Let us take pre-cellular, and the system is called MTS or IMTS, and that stands for manual telephone service, and this stands for improved manual telephone service. Now, what that means is that a person in their car, and the reason I say that is the radios were about 1.5 feet long, 20 watts, and there's in Cleveland about 7 channels. That's right, precursor to cellular had 7 channels. Pick up the phone, and the base station equipment would indicate to the operator that somebody was requesting service. The person would tell the operator what number they wanted to call. The operator would place the call, start the clock, then patch the car electronics into the POTS electronics, plain old telephone service. So there's operator intervention here, and in the improved service is that the car could basically call the base station in control with the number, and that would automatically connect into the telephone network and remove the need for the operator to place the call. So in Chicago, a new and improved system was trialed and went into service about 1984, and this was called AMTS, or Advanced Mobile Telephone Service, and it's based on cellular technology. Now, if we go back up to here, what we have is a 200-watt base station which basically can cover all of Cleveland. And located in the suburbs and downtown, there would be satellite receivers. These receivers would connect into the electronics associated with the base station and select the least noisiest signal to be the one that is passed along to the person on the telephone network. So channel reuse was an issue. Here's Detroit, and they had one channel allocated on the same frequency. And in the early mornings, there was absolutely no difficulty for that Detroit signal to ingress into the Cleveland signal. So the issue is when you're dealing with 200 watts, it goes a long way. Now the cellular system, on the other hand, has very low power transmitters. And obviously from the cell phone, it can't be too big because you hold it in your hand, and it permits what's called frequency reuse. And this is usually drawn as a hexagonal pattern, and then in some areas where there's a lot of people, they can actually break this down into sub-cells. So with channel reuse, say we can use the same frequency channel 1 here and here, and they won't interfere with each other because they're low power. Seeing that cell sites are relatively close together, you don't need a whopping 20-watt transmitter to hit the cell tower. So that's the whole purpose of it, is frequency reuse based on reducing the power of the base transmitter and also of the portable guy. So these came out of cars and went into pockets. First cellular radio I used was about this big. It was on the job. Looked like a radio, had an antenna sticking out of it. Anyway, amps used frequency modulation to begin with, and then it advanced a lot. And it went into different modulation schemes, and one was frequency hopping, and the other is code division multiple access, and both of these allow a lot of people to talk on a channel. Now for the CDMA, this guy, it's 1.22 megahertz bandwidth, and 63 to 64 people can talk on it, and a channel or two is used for the pilot channel. That is, when you turn on your cell phone, it goes to that pilot channel and says, I am here, and then that registers, so if you receive an incoming call, it will go to the pilot channel, contact your cell phone, negotiate with it, and tell it what frequency to switch to in the cell. When it does that, then your connection has been completed and you can talk. As you drive out of the center of a cell, there's hard and soft handoffs. So all the electronics behind the scene have to get that landline switched over to the transmission system in cell 5. It can be abrupt, hard handoff, or soft, where you're receiving both signals at the same time. So it's very, very fascinating technology, and it's amazing how much can be done with cellular telephones. I'm amazed. It almost seems impossible. Anyway, that should conclude for detection of frequency modulated signals, and thank you for watching.